Hello students, in this video we'll introduce the notion of a Cauchy sequence. A sequence of real numbers an goes from 1 to infinity is called a Cauchy sequence if the following condition is true. If, for every epsilon greater than 0, there is an n epsilon, which is a natural number, such that, and here's the Cauchy condition. The Cauchy condition says that an minus am is less than epsilon if n and m are bigger than or equal to this n epsilon. Okay? So these are what Cauchy sequences are. They satisfy this condition. Unlike the definition of a convergent sequence, all Cauchy is saying that the deeper you are in the expansion, the difference between any two terms is getting arbitrarily close to each other. This is a little bit different than the definition of convergence, but we'll see for real numbers it's actually the same. So let's prove that first proposition. That's our proposition for Cauchy sequences. And our proposition is that if the sequence n goes from 1 to infinity is convergent, then the sequence n goes from 1 to infinity is Cauchy. Okay, so convergent sequences are Cauchy sequences. Let's prove this. Proof: let epsilon be greater than 0 and pick an epsilon in n such that what? Such that an minus a, the limit which we know exists by the definition of convergence, is less than epsilon over 2 if n is bigger than or equal to n epsilon. Okay? And now, let me suppose, here's the big part, suppose that both m and n, that n and m are both bigger than n epsilon, then x, or let's say an minus am is equal to an minus a plus a minus am. And I can triangle inequality this and say this is less than or equal to an minus a plus am minus a. Since both m and n are bigger than n epsilon, these are both less than epsilon over 2. So that's less than epsilon over 2 and epsilon over 2. So that's a total of just epsilon. So an minus am is less than epsilon if n and m are bigger than epsilon. So this allows us to conclude that the sequence an is a Cauchy sequence. So convergent sequences are Cauchy sequences. That's our proof. And then we'll see in further videos that actually, using Bolzano-Weierstrass, we can conclude that if you are a Cauchy sequence, then you must also converge. And that's going to stem from one further property, which is an easy exercise to see. And that property is that Cauchy sequences are automatically bounded sequences. So the final proposition, which will lead to a future video to prove, is that Cauchy sequences are bounded. Okay, and that basically follows the exact same line of reasoning as it does for convergent sequences, which we'll see in a further video. Thank you very much.